Everyone, welcome to this part. Now let's go into how to determine the rate law for a given chemical equation. Here we're going to study initial rate law method. So what we're going to study in this part is now initial rate law, initial rate method. First one, let's keep in mind that rate should be determined experimentally. The balanced overall equation does not give us the rate. The coefficient does not match the reaction order. So for this method, we need to set up the chemical equation and we change the initial concentration at a time. Many times we repeat this reaction, maybe 3 times, 4 different experiments, changing the initial concentration at one time. When you have 2 or 3 reactants, we change just one concentration, one reactant to see the effect of this reactant, and we change and then measure the initial rate to determine the reaction order. Let's see an example. Very simple example. We have one reactant here, genetic equation, reactant A. Reactant A now dissociates to form products. Now we change the initial concentration of reactant A, 0.10 molarity, 0.20 increase double, 0.40 increase 4 times, and then we repeat the reaction 3 times at the same condition. We only change the initial concentration of A, temperature and all the other conditions are the same. Then we measure the initial rate. So in per second, how much of the molarity of A is changing initially at just when the reaction just starts. When we measure it, we found that it is 0.015, 0.060, 0.240. Now determine the order of reaction with respect to each reactant and the overall order. Write the rate law for the equation for the reaction and determine the reaction coefficient K. What we need to do is now first figure out rate is now proportional to the concentration of the reactant A. Reactant A to its power A. This small a, we call this one reaction order, and then reaction coefficient K. So apply the rate law to each experiment. Experiment set 1, apply this one. Initial rate is equal to K times the concentration to the power of A. Same thing to experiment 2, experiment 3. Now, in order to find out this A, now take the ratio between the rate law to calculate the reaction order A. For example, let's divide by equation 2 by 1 each side. So get the ratio of 0.060 divided by 0.015 is equal to K times 0.20 to the A divided by K to the 0.10 to the A. Then here in this equation, this formula, K cancels out. K is the same, and then because the power is the same, we can put this one base together, 0.20 over 0.10 to the A, which is 2. So 2 to the A. So 0.040 over 0.105 is equal to 2 to the A. This value, when you calculate it, just 4. 4 equals 2 to the A. 4 is now, we know that it is 2 square. So then 2 square is equal to 2 to the A should be 2. So in this way, we determine the reaction order is 2. Next step is now, we repeat the same thing for reaction 3 and reaction equation experiment 3 and 1. We find the same result. 16 is equal to 4 to the A equals 2. So we found out the reaction order is 2. Next one, insert the value of A. This is 2 to any equation. Here or here you'll have the same result. And then we can determine the value of reaction coefficient, constant K. So we are using this equation 1. 0.015 equals K times 0.10 square. 0.10 square is now 0.010. So we divide by 0.010, both inside found out K is now 1.5. So here rate is molarity over second. A is now molarity square. So when you divide it, it is molarity. This one per second. This is a typo. Molarity 1.5, molarity -1 as the times to -1. That should be the value of K. Now we go to a little bit more complex example. Now we have three reactants. So bromate reacting with bromide and acidic condition, they react together to form bromine and water. So 4 experiments were conducted to find out the reaction order and the reaction rate. Determine the order of reaction and write the Rayleigh law, find the value of K. So the data is shown here. The data, 4 different sets of experiments conducted. Initial concentration of each reactant was changing. Initially 0.10, 0.10, 0.10 molarity. Second one, this one, bromide and hydrogen ion concentration same, but bromate ion, the concentration was doubled. And then third one is bromate and hydrogen ion concentration same as 1, but the concentration of bromide was tripled. And the fourth one is this concentration. The measured initial rate for consumption of bromate was measured as 1.2, 2.4, 3.5, 5.5 millimolarity per second. Now, put this one, translate into this one, and let's calculate the reaction rate. First, rate, remember rate is now reaction constant multiplied by the reactant to the power of A, second reactant power of B, third reactant power of C, and then plug in each one, each experiment 1, 2, 3, 4 into this general equation, rate equation. Then we have this equation. For example, this one, 1.2 is equal to K times 0.10 to the A, 0.10 to the B, 0.10 to the C. Similarly, 2.4 is equal to, for here 2.4 is equal to 0.2 K times 0.20 to the A, 0.10 to the B, 0.10 to the C, and so on and so forth for experiment 3 and 4. Now, take the ratio between this equation 1, 2, 3, 4 to find out the reaction order A, B, and C. First, let's calculate the order of A. In order to find A, then we need to see which experiment set does this bromide and hydrogen ion same, and only change in bromate ion, which is experiment 1 and 2. Now let's get the ratio between equation 2 and 1. So the rate is 2.4 divided by 1.2, and it is K times 1.20 A to the A, 1.0 B, like this way. And then when you see this ratio, K is the same, canceling out. 0.10 to the B, 0.10 to the C, they cancel out. The only remaining portion is now 0.20 divided by 0.10. So the base is same, we put the base together, 0.20 over 0.10 to the A, which is 2 to the A. Then this part, 2.4 divided by 1.2 is now 2. 2 equals 2 to the A, we can determine A should be 1. We do the same thing. When you compare equation 3 and 1, we see that only bromide ion is changing. So bromate, hydrogen ion concentration same, so we can determine the reaction order B. So 3.5 over 1.2, 3.5 over 1.2 equals K times the reaction rate, like this one. K cancelling out, 1.10 to the A cancelling out, 0.10 to the C cancelling out. We have only 0.30 over 0.10, which is 3 to the B. So this value, 3.5 over 1.2 is now 2.92 equals 3 to the B. In this case, in order to calculate this kind of exponential equation, we take a common logarithm on both hand sides. Then log 2.92 equals B times log 3 to the B. Then by the property of logarithmic equation, we can take out expression. We can take out B to the front. B times log 3. Now let's divide by both sides by log 3. B is now log 2.92 divided by log 3, which is 0.972. Because the order should be an integer, usually 1 and 2, or sometimes 0, or sometimes half, 2 2/3. But in this case, 0.972 is close enough to 1, so then B is 1. Now let's do the same thing. Let's think about C. Now let's calculate C. So 0.20, 0.10. So experiment 2 is not very similar. So A, bromate and bromide ion concentration same, only hydrogen ion concentration changes. So we compare experiment 2 and 4 together. The ratio equation 4 and 2 is now the rate 5.5 over 2.4, K times the reaction expression of rate, and K cancelling out, 0.20 cancelling out, 0.10 cancelling out, only 0.15 divided by 0.10 to the C power. So then 1.5 to the C is now 5.5 divided by 2.4. When you calculate this ratio, it is 2.292 equals 1.5 to the C. As before, we take a common logarithm on both sides. Then log 2.292 is now C times log 1.5. So divide by log 1.5 on both sides. C equals log 2.292 divided by log 1.5, 2.05, close enough to 2. Then we find the reaction order C is now 2. So like this way, we find the rate, the reaction order for bromate is 1, for bromide is 1, and then hydrogen ion is now 2. Overall reaction order is now, addition of all this reaction order power is now 4. Now let's move on to calculate the rate constant K. The rate, generic equation now, here rate is now K times bromate concentration, bromide concentration, and hydronium ion concentration to the square. Now let's calculate K. In order to do that, we just use any of this equation. So we can use 1, 2, 3, 4. What is most simple? Let me use this one to find out the value of K. So 1.2 is now K times 0.10, 0.10, 0.10 square, which is 0.000110. So let's divide by both sides. This value, it is 12,000. K is now 12,000. The unit is now the unit rate, which is millimole over liter second, and divide by millimole, mole per liter to the fourth power. Mole per liter square, so mole per liter to the fourth power. So then mole per liter cancels out. Milli is remaining. What is milli again? Yes, milli is now 10 to the negative 3 power. So 10 to the negative 3 is right there. Mole per liter canceling out. This one becomes 3. So molarity, mole per liter is molarity to the negative 3, because this one is denominator, mole per liter to the negative 3, and second to negative 1. And 10 to the fourth power multiplied 10 to negative 3 is now 10. So finally, K is now 1.2 times 10, 12. 12 molarity to negative 3 per second. That's the value of K. This way, we are able to calculate the rate law for this equation, for this reaction. Now, let's take time to find the rate law for consumption for this equation, nitrogen oxide and oxygen forming nitrogen dioxide, and determine K for 3 sets of experiments. Change the initial concentration of nitrogen oxide and oxygen like this way. The initial rate was measured. Please take time to calculate the rate law and the value of K.